Hey everyone, welcome back. Today we're jumping right into an in-depth analysis of a technology that completely surrounds us, yet honestly it remains almost entirely invisible to the naked eye. We're talking about the silent revolution of electric motors. Just think about it for a second. From the vibration of your smartphone alarm waking you up, to drone propellers blurring up in the sky, all the way to those massive electric vehicles accelerating silently down an open highway, every single one of these relies on the exact same fundamental piece of engineering. In this explainer, we're going to tear down the walls of that engineering and see exactly what makes it tick.
Okay, let's dive into this, because really, this is the ultimate engineering mystery, right? How exactly do we take raw, completely invisible electricity flowing through a wire and convert it into heavy, powerful, physical work? I mean, how does a current turn a wheel? Well, to master this, we have to strip away all the complex machinery and look at the absolute baseline physics that govern the entire system.
Part 1. Invisible Power, Basic Magnetism. To truly understand the machine, we first have to understand the fundamental concept of attraction and repulsion. It all boils down to a very simple, invisible game of push and pull. As you know, every single magnet has two distinct regions, a north pole and a south pole. And the absolute law of magnetism dictates that opposite poles attract each other, while identical poles violently repel each other. This invisible zone of pushing and pulling forces surrounding a magnet is what we call the magnetic field. But here's the catch. A permanent magnet on its own can't create a motor. We need something we can actually control. And that's exactly where the electromagnet comes in. If you take a simple copper wire, wrap it into a coil, and pass an electric current through it, boom, you've just created a temporary magnet. The real genius here is that if you reverse the direction of the electricity, the magnetic poles immediately switch places. North becomes south, and south becomes north. This introduces us to the Lorentz force law. Essentially, this law states that a moving electric charge inside a magnetic field experiences a physical perpendicular pushing force. This invisible push, that is the exact muscle of our motor.
Part 2. Anatomy of the stator and rotor. Now, what's really interesting about this slide is the sharp contrast between the motor's two fundamental components. On the outside, we have the stator. Just as the name implies, it's the stationary outer shell of the machine. Its one and only job is to provide a uniform, highly concentrated permanent magnetic field. Then, on the other side, suspended directly inside the hollow center of that stator, is the rotor. Sometimes you'll hear it called the armature. This is the spinning heart of the motor, usually made of a metallic core wrapped tightly in hundreds of turns of copper wire.
So what happens when you turn it on? When electricity flows into the rotor's windings, it instantly transforms into a powerful electromagnet. What happens next is basically a violent mechanical dance. The rotor's newly created magnetic field is instantly crushed and pushed by the permanent magnetic field of the stationary stator. Because identical poles repel, the stator violently pushes the rotor away, creating a heavy twisting force that engineers call torque. And this torque is exactly what forces the central shaft to rotate and actually spin a wheel or a blade.
Part 3. The role of brushes and the commutator.
But right here we run into a massive engineering hurdle, the lockup problem. As the rotor twists to line up its north pole with the stator's south pole, it naturally reaches a point of total equilibrium. All the forces just balance out, and the moment it reaches this perfect alignment, the rotor wants to completely freeze and stop moving altogether. So the crucial point is that we must constantly flip the magnetic polarity of the rotor right at the exact moment it passes that halfway point. To do this, engineers designed an extraordinary mechanical switch. As the rotor spins toward that freezing point, the physical connection to the battery briefly shifts, reversing the electrical flow by exactly 180 degrees. North becomes south again, the repulsion continues, and the rotation is saved.
This ingenious solution relies on two key components, the commutator and the brushes. The commutator is a highly conductive copper split ring mounted right on the rotating shaft. The brushes, on the other hand, are stationary, spring-loaded blocks made of soft carbon. They press gently against the spinning commutator, basically acting as a physical bridge. As the ring spins, it continually changes which segment touches each brush, automatically reversing that current flow and keeping the rotor spinning indefinitely. I mean, it is just pure mechanical genius.
Part 4. Brushless motors and the digital brain.
Now, while the classic brush motor absolutely changed the world, it has a critical, inherent flaw. And this brilliantly illustrates that problem: severe mechanical friction. Those carbon brushes are constantly rubbing against spinning metal, which creates carbon dust, audible noise, and dangerous bright electrical sparks. So what's the solution? The brushless DC, or BLDC motor. Engineers essentially flipped the entire motor inside out. They took the permanent magnets and moved them to the spinning rotor in the center. Then they took the electroconductive copper coils and moved them to the stationary outer stator ring. Because the coils are now locked in place on the outside, we no longer need a spinning commutator at all, and we completely eliminate those physical sparking brushes. The result? No friction, zero maintenance, and vastly higher speeds.
But you might be wondering, without physical brushes, how on earth do we flip the current to keep the magnets pushing and pulling? Well, the answer is a modern digital brain called the Electronic Speed Controller, or ESC. The ESC acts as a completely digital commutator. It uses Hall effect sensors embedded right inside the stator to perfectly track the exact position of the spinning magnets. It then fires electricity into the stator coils in a precise rotational pattern, smoothly pulling the rotor along in a completely frictionless environment.
Part 5. Motor Technologies Shaping the Future. Let's move to and see how this builds into the technologies that are literally shaping our future right now. These incredibly efficient digital frictionless motors are no longer just industrial tools. They are our frontline weapons in the real-world fight against climate change. To put that into perspective, a state-of-the-art gasoline engine wastes about 70% of its energy just as heat and friction. In stark contrast, modern electric vehicle drivetrains achieve well over 90% thermal efficiency. Furthermore, they can perform an absolute engineering miracle: regenerative braking. When you lift your foot off the accelerator in an EV, the digital controller reverses the flow of energy. It actually turns the electric motor back into a generator, using the car's kinetic energy to slow the vehicle down while pumping clean electricity straight back into the battery pack. It's a total game changer. The sheer elegance of this technology is staggering. We've gone from simple laboratory wire loops to hyper-efficient digital machines driving global transport. And the innovation isn't stopping anytime soon. Engineers are currently developing ultra-thin axial flux motors that offer massive, mind-blowing power right inside the wheels of vehicles. So I'll leave you with this thought. As we continue to eliminate rare earth magnets and push power density to the absolute extreme, how far will this silent magnetic revolution push the boundaries of human transportation and clean energy? Think about that the next time you hear the silent hum of an EV driving by. Until next time, stay curious and keep learning.